Constrained Visual-Inertial Localization with application and benchmark in laparoscopic surgery. The camera localization task is to find the transformation between camera location C and fixed location T. We assume a calibrated stereoscopic camera. At detection time T', we triangulate stereo matches that fulfill the epipolar geometry. The reconstructed points are inserted into a 3D map that is attached to the detection frame. Matches in the 2D image plane, here denoted U, are found in the consecutive frames. The camera movement is then reconstructed by finding a set of points that fulfill the epipolar equation. This is a typical visual odometry approach. We, however, tackle applications where the image content is moving or the image quality is so low that the algorithm loses tracking. Therefore, additional information needs to be taken into account. The inertial measurement unit gives us 3 residuals. 2 static directions we can align the rotation part with, as well as a rotation update based on angular velocities. Our algorithm is further designed for applications where the solution space is reduced. A constraint on the movement can reduce the solution space from 6 to 4 degrees of freedom, and we build a residual that penalizes solutions not fulfilling this requirement. Following state-of-the-art methods, we then jointly optimize over all the residuals. At first, the weight alpha is adjusted. We weight by the determined variance and also by the number of residuals for each sensor type. To let the cost function parts decrease simultaneously, we up and down weighted different sensor types using a trait of parameter gamma. Here, green is the ground truth and red is the output of our method, and the T lines are the rotation obtained by IMU measurements. The green dot is the pivot point, and the line attached to each camera should go through it. Now, the image quality was really low, and every SLAM algorithm loses tracking. Most importantly, our algorithm now relocalizes the camera without finding descriptor matches or conducting image alignment, as it is done in direct methods. Furthermore, the huge dynamic part was filtered out, since it was not aligning with other information from IMU or motion constraints. The map points move as soon as their extraction frame is optimized. After optimization, the map is realigned and the geometry is observable. For promoting research on the application of minimally invasive laparoscopy, we created a dataset which is publicly available. During data acquisition, the infrared tracking device generated the ground truth. We further provide full calibration and time synchronization, such that the data is ready to use. Its contained information is comparable to state-of-the-art SLAM benchmarks, and we registered a DOI, making it uniquely assignable and unmodifiable. Thank you very much for your attention. Here we listed our main contributions, which can be separated into 2 main parts, the novel algorithm and the calibrated clinical dataset.